Hi guys, welcome to this set of videos. Okay, what we've been doing here is we've been going through several sections where we've been talking about proving whether triangles are congruent, right? We started off by talking about CP, CTC, corresponding pairs of congruent triangles are congruent. But that turned out to kind of be a cumbersome process, right? Because you had to prove a lot of different things. You had to prove that 3 corresponding sides and 3 corresponding pairs of angles were all congruent in order to show that triangles were congruent. That was a lot of work. And so what we've been doing the last couple of sections is looking at shortcuts, right? We looked at the angle side angle theorem, which essentially cut the amount of work we had to do in half, telling us that all we had to do was prove 2 corresponding pairs of angles and an included side was congruent to prove that triangles were congruent. And then a section ago, we looked at the idea that the side angle side, if you could show that 2 corresponding sides and an included angle were congruent, that was enough to prove that the 2 triangles were congruent. Turns out, there's another shortcut, and we're going to talk about it here in this section. So, your essential question, as we always start out with, is this. What does the SSS, triangle congruence theorem, tell us about triangles? Well, again, SSS, you got it. It's side, side, side. And we've been doing this enough. I think you guys are seeing the pattern. Here's what this is saying. If you can show that all 3 sides of 2 different triangles are congruent, the corresponding side or the corresponding pairs of sides of let me say it this way. The 3 corresponding pairs of sides of any 2 triangles are congruent, then you've proven that those triangles are congruent. Again, I apologize. Slight typo in there. Just cross those out. Give me side, side, side. Again, side, side, side. And again, side, side, side. Same objectives or learning targets as we've seen before. First, we're going to talk about the side, side, side congruence theorem. How does it work? Why does it work? Then you're going to go ahead and use that to prove that triangles are congruent. Of course, just like we've been doing all year long, because I also teach algebra, any chance I get to do algebra with you, we're going to do it. And so we'll use it to find the missing side lengths and angle measures of congruent triangles. So here we go. Let's just jump right into this. All right, the side, side, side congruence theorem. Here's how it works. Okay, first, the theorem. If 3 sides of one triangle are congruent to the 3 sides of another triangle, then those triangles must be congruent. So here's all you need to do. You just need to show that the 3 pairs of corresponding sides of any 2 triangles are congruent, and you've proven that those triangles are congruent. Now, why? Why does it work? Well, here's the reason why it works. Let's consider these 2 triangles. Please notice side DE is congruent to side AB. And side FE or EF, whichever way you want to say it, EF, is congruent to BC. And finally, side FD is congruent to side AC, right? That's what all those little hash marks mean. Well, here's all I'm going to do, right? I'm just going to take this guy, bring him over, and set him down right there, which is exactly what I've done right here, right? Since since side DE and AB, right? Since those are corresponding sides, they're the same length. Just put those guys together, and there we go, right? This is the red triangle on top, the blue triangle on the bottom. Now, here's why. All I have to do is show congruence of the 3 sides in order to prove the triangles are congruent. Follow me on this. The exact same diagram on the next page. Here's what you're going to do. I know, here's what I know, right? Look, I know that the length of DC, this guy right here, DC, is the same as the length DF, right? I know that because it's given to me, right? The double hash and the double hash tells me those sides are congruent. They're the same measure, right? Well, guys, think about this for a second. Think back a couple of chapters ago, we talked about the definition of a perpendicular bisector. And here's what we said. We said the definition of a perpendicular bisector is that any point on that bisector is equidistant. Let me draw you a quick little picture right over here. Okay, if this line is a perpendicular bisector, here's what I know. I know that these two segments are congruent, and by definition, any point, pick any point you want to on that perpendicular bisector. I don't care where it is. You can pick a point up here, you can pick a point down here, you can pick a point right here in the middle. It doesn't matter. Pick any point you want to. By definition, any point you want on that perpendicular bisector is equidistant, meaning an equal distance from point A and point B. So let's just say I happen to pick, I don't know, this point right down here. Again, the definition tells me that that point is the same distance from point B as it is from point A. It's equidistant. Hopefully you guys remember that definition of a perpendicular bisector. Again, that was a couple of chapters ago that we got that definition. If you didn't remember, there it is, right? Point D is equidistant from F, D, right, as it is from C. So what we've got, right, is since D is equidistant from F and C, it must be on the perpendicular bisector. So that's exactly what I tell you right here. Where did I put it? Yes, right there, right? Therefore, point D lies on the perpendicular bisector of CF. CF is this guy right here. Okay, so what we've got then, right, is D lies on the perpendicular bisector of CF. One more. Same idea for E, right? You can show the same is true for point E. Let me use a different color, right? E, this distance right here from E to F, is the same as the distance from E to C, right? I know that because 3 hash marks, C, 3 hash marks, right? That tells me that they are congruent. So EF and EC are the same measure, the same length. Well, again, by the definition of the perpendicular bisector, that means that E must be on the perpendicular bisector of FC. Now, here's the conclusion, right? Knowing then that this guy right here, DE, is the perpendicular bisector, what that means is if I were to take, right, this triangle on the bottom and flip it up, C and F are mirror images of each other, right? This means that the reflection across the line DE, across this line, right? The reflection, right, would map point C, maps to point F. They're mirror images of each other, right? And what that does is proves these two triangles are congruent. So by showing that all three pairs of corresponding sides are congruent, you know the triangles must be congruent, right? Thanks to this definition of any point lying on a perpendicular bisector. Okay, knowing that, take a look at a couple of example problems. Here's what we've got. I got a couple of triangles here, and we're going to go ahead and see if we can figure out, oh, check this out, right? If I take this triangle and I flip it over, slide it up, I've got corresponding sides. That guy corresponds to that one. This one corresponds with this one, and this one corresponds with this one. And so there we go. Let's go ahead. I'll do them in the colors that we've got there. I know that side AB is congruent to side DE. I know that side AC is congruent to side DF. And I know that side BC is congruent to side EF. So, since I have now shown, right, based on my diagram, based on the diagram I was given, that all three pairs of corresponding sides are congruent, the side-side-side theorem shows that these two triangles must be congruent. Let's keep going. I got a couple more here for us. Let's see what we've got. Okay, taking a look at this guy, it looks like, right, all you'd have to do is take this triangle right here, right, rotate it down, right, and those two guys would lie on top of each other. So here's what I've got. I've got that side EH corresponds to side HG. I've got side DH corresponds with side FH, and side ED corresponds with side FG. And that's it. That's good enough. That's all I need. Three sides. So I have, let me write that out for us here. Side EH corresponds to GH. In the red, I have DH corresponds to FH, and I have DE corresponds to FG. And they're congruent, right? EH is congruent to GH, DH is congruent to FH, and DE is congruent to FG. I've shown that the three pairs of corresponding sides are all congruent, and so the side, side theorem. Awesome, fantastic. I got one more for us here. Let's see what we got. It looks like if I take this triangle, I flip it over and then slide it over, right? Those two guys would lie on top of each other. So if I flip this guy, actually, actually, no, it wouldn't be a flip. Do you see that? I'm going to actually have to spin it, set it down over here, so that MP and SQ or QS, those are corresponding sides, those guys right there. That means that RQ is corresponding to MN, but look, right? 28, 32, not the same. Now those guys are. Right, but guys, that's not enough. Right here, I've only been able to show that two of the three pairs of corresponding sides are congruent. I have to show that all three corresponding pairs of sides are congruent, and I can't. So, because right here, MN is not congruent to RQ, I know that these two triangles are not congruent. Triangle MNP is not congruent to triangle RSQ, and I know that, right, because I just showed that one of the pairs of corresponding sides not congruent. 28 inches, 32 inches, that's not the same. Different measures. So because those sides are not congruent, I know that these two triangles can't be congruent. All right, guys, head on over to the next page of the notes. I got a few more example problems for us to take a look at together, and I'll meet you guys over there.